clicking on the chat icon at the bottom of your Zoom window. Don't forget to choose all panelists and attendees from the drop-down to talk to everyone attending the session. Have a question for the speakers? Click the Q&A icon and type your question here. Or give a thumbs up to another question. That's all there is to it.
All right, thank you all for joining us today for a closer look into high-performance home strategies and solutions, master session for IBSX 2021. My name is Joel Martell, and I work with the North American Insulation Manufacturers Association, and I'll be your moderator for this session. With us today, we have Steve Easley and Gordon Cook. Steve is the owner at Steve Easley and Associates and has been working on building solutions longer than I've been alive, and Steve specializes in solving building science problems and helping educate the building industry professionals. Gord is a professional engineer with over 25 years of experience and is a partner at Construction Instruction. Gord specializes in low and high-rise residential construction practices, and his ability to translate complex building science issues and solutions to audiences is uncanny. Next slide. Now let's take a look at what these guys will be covering today. So in this session is going to show builders and design professionals how to use high performance strategies to avoid callbacks and warranty claims. These gentlemen are going to investigate common issues regarding energy efficiency, moisture management, air sealing, and ventilation. And they will look into ways to make high performance homes more affordable by understanding how a house can operate as a system to empower a builder to work more effectively with the trades to implement these high performance solutions. Next slide. A few learning objectives for today's sessions are going to be gain insight into common sense air sealing processes and proper ventilation strategies, while also learning tips for effective and efficient installations that meet or exceed code. Review how to make small adjustments to common existing details that can lead to significant improvements in energy efficiency, comfort, and durability. Recognize and attain the critical balance between cost effectiveness, structural integrity, energy efficiency in home design and construction. Discuss popular callbacks that builders receive and how to avoid them. Next slide. So a quick disclaimer for today's education session. I'll go over this briefly. So the topics discussed and the content of this presentation are for informational purposes only and are not intended to be construed as exhaustive presentations of specific information or advice on any specific topic. Building designs, construction practices, building codes, and climate conditions vary widely throughout North America and the rest of the world. Construction practices must be adapted accordingly. Viewers are strongly advised to seek counsel with local expertise and follow all local codes requirements regarding any projects. With regard to any information presented, Steve Easley and Associates, LLC, and Construction Instruction, LLC does not make any warranty, express or implied, and specifically disclaims any legal liability or responsibility for the accuracy, completeness, or usefulness of any information, product, service, or process presented. Steve Easley and Associates, LLC further disclaims legal liability and responsibility for any loss, damage, or risk, personal or otherwise, incurred or created as a consequence directly or indirectly in the use or application of any of the information or materials presented in this presentation. Now, just before we begin, as a reminder to folks, you can type questions into the Q&A feature. You also have the ability to like certain questions throughout the presentation, so that gives it a higher priority. We will be stopping periodically to address some of the questions throughout the presentation. So I encourage you to type any questions that you have there and keep an eye on that. So now I will turn it over to Steve and we can get started.
Thank you, Joel. And we really appreciate everybody joining us today. We believe that we put together a series of slides and presentation that you'll find helpful in building high performance homes. Building high performance home doesn't have to be expensive or complicated. And we're going to go through a lot of the basics today and understanding how to do this cost effectively. Really, high performance success really depends on measuring true performance of all the energy efficiencies along the way and doing intermediate evaluations. We don't simply rely upon modeling, because at the end of the day, oftentimes homes don't actually perform as they're modeled. And thirdly, we don't want to assume that trade professionals are knowledgeable and can do the work that truly performs. So this whole concept about integrated design and thoughtful planning is followed by careful implementation is critical to really building high performance homes. And inspecting and measuring phase by phase each step of the way is really key. So you want to have quality control and quality assurance. And if you don't measure, you don't know. And it's really not about a bunch of whiz-bang technology or ridiculous amounts of insulation to make high-performance homes. We're going to go through the step-by-step simple things that you can do to really achieve high-performance construction. That really starts with just being observant. Here's a typical picture of job site I was on a few months ago. And if you look at this, you want to get in the habit of saying, oh, what's really wrong with this picture? And if you look at this, this is obviously the builder spent some money on some expensive windows. But then when is this home really going to perform as much as it could be? And if you look over here to the right, we see that we've got, ductwork that's uninsulated inside exterior cavity walls. We have an awful lot of plumbing, electrical spaces in the cavities, which means there's not going to be room for the insulation. The building is overframed. We don't need to have that much lumber. And so there's just lots of small things that we can do to really make homes high performance. For example, we're building, consulting on homes out in the Central Valley of California, and these are zero net energy homes that we're working on for Habitat for Humanity. And we're building these homes cheaper than they were before, and they're all zero net energy homes. That really starts with, understanding how you integrate integrated design. And that means everybody getting on the same page before construction starts, so that we don't have situations like this that happen in the field. So what often happens is if we don't plan ahead and we don't think ahead, people in the trades are going to make it work however they have to make it work. And so here, for example, you can see we have a supply duct that's completely crushed by plumbing. And that's all about not thinking things through in advance. And so what we hope to accomplish today is, open your eyes to some of the things that you could do to truly make homes better performing. And it's not about how many homes a year that you build, or for that matter, how much money you make in terms of what makes you successful. What makes you successful is how much money you get to keep. And how much money you get to keep is determined by how well you control your callback costs. So building high performance homes not only gives your customers homes that are energy efficient, durable, better indoor air quality, it also helps your bottom line, fewer callbacks. And so simple things like using trusses instead of standard floor joists allows HVAC contractors to run the ducts any which way they want, and you're not, curtailed on the job site by people making decisions that can really impact the overall performance. And like here's an example of this not thinking things through. Here we have the HVAC guy had to figure out a way to box around this floor truss because nobody mapped this out in advance. So that has a big impact on performance. So I'm a real big believer in inspections and quality control. And I think if I were to ask, I tell my builder clients, I said, you should do 3 major inspections or at a minimum. And one is just before cladding to make sure that your weather barrier and all your flashing is done properly. Gord's going to talk a little bit about that later. But here's an example of a home that's perfectly wrapped. The windows are perfectly installed. Everything's flashed correctly. And you want to make sure the building is completely dried in, before the cladding's installed. Another inspection is just before insulation, and that's so you can find out where all the air leaks are at. And then a third one is just before drywall, so you can make sure the insulation's installed right. If the vapor barrier is required, you can make sure that that's installed in such a way that it has the integrity that's needed to make this work. Here's a great example of a project I was on, and I simply, saw some wiring, and I pulled back the insulation, and sure enough, it reveals a pretty good sized hole. And so this is why we want to make sure that we do an air barrier inspection before drywall's installed, and then before the insulation's installed, more importantly. So when I think about the kind of the top 8 reasons that I see every day in my field investigations of why homes don't perform, number 1 is not controlling air infiltration, having an ineffective air barrier system. 2, high framing factors and thermal bridging. We see homes that have framing factors of 25 to 30%. And the homes that we're doing in the Central Valley, for example, we have framing factors down to 11 or 12%. That saves a lot of money, particularly in today's climate where lumber prices are through the roof. High window to wall area ratios have an impact. Poor glazing choices, not getting the right windows for the right climate. Poorly installed insulation, focusing too much on the cavities in terms of how much insulation instead of how it's installed. Certainly having poorly designed and installed HVAC systems has a huge impact on performance and comfort. And then oftentimes hot water and lighting are afterthoughts. So if you're looking for 8 areas to really focus on, these are the ones I find that are most important. Focusing on building enclosure really helps us in the sense that it, number one, reduces the size of the heating and cooling system, energy use, obviously, and costs and all the issues associated with that. So focusing on the building enclosure first is one of the most cost-effective things we can do because, you know, the building enclosure lasts the life of the structure. Energy savings typically don't diminish much with age. You can manage moisture and increase building durability and enhance indoor air quality by focusing on the enclosure. And it has the biggest impact on overall comfort. So getting the envelope right is really, really important. If you look at the image on the left here, you can see where all the frost is melting is everywhere that we have significant amounts of thermal bridging. Almost all the codes now are moving towards exterior insulation. And so we need to understand how to install that in a way that doesn't lead to water and moisture problems. Image on the right, obviously, is an infrared image of a building that's not performing very well. So I think it's important that we focus on those 4 control layers. And if you break down your structures into these 4 areas and always understand that these are really critical to overall performance is number 1, our weather resistant barrier. We spend roughly $13 billion a year on construction related defects. And most of those lawsuits are due to water related issues, getting the weather resistant barrier and flashing right. With exterior insulation being added to, you know, the building envelope in many cases now, even required by code, and certainly future versions of the code, rain screens are going to be more important in terms of being able to solve these water and moisture issues, and we'll get into that a little bit later. Also, next layer is our air barrier and air sealing. That's really critical. Then our thermal layer, which is interior and exterior insulation. And then in climates where vapor barriers are retired, really understanding how those work and how to install those properly. First, let's talk about controlling air infiltration, because that is really key to comfort, energy efficiency, and overall building performance. And it's one of the areas that I see are almost always overlooked. We tend to think that if we just put a building wrap on the outside of the building, that sort of solves all of our problems, and it couldn't be further from the truth. Today's codes almost require that we build homes to 3 air changes an hour on most parts of the United States, and getting down to 3 air changes an hour requires some thoughtful thinking and looking for things other than just, you know, a building wrap alone. Oftentimes we think that if we insulate, you know, that solves the problem. Well, insulation in itself is not a very good air barrier. And one of the areas that's most cost effective to focus on is the attic area in terms of air sealing. You know, we have so many penetrations in attics with can lights and ducts and all types of penetrations that has a huge impact on overall building performance. And so again, it's important that you have an exterior building wrap, but we also have to focus on every part of the building envelope when it comes to air sealing. A great example of this is a home that I used to own. This was a 3,400 square foot house, and it was built in the 1970s. And I had a bat problem in the attic, so I thought, well, what a better time to fix things than to an air seal than after all the insulation's pulled out. So we pulled out all the insulation, and then did a blower door test. And this house, again, is about 3,400 square foot, 2-story home. And the blower door test yielded about 4,460 CFM of leakage. Fairly leaky house, but pretty typical for a house that was built in the 1970s. So I went forth and air sealed everywhere, and some of the areas that most people don't think about when it comes to attics. And it's really cost effective and easy to do this before the insulation is installed, is to make sure that we air seal all the penetrations and even interior wall plates, because even the interior walls have a fair amount of air exfiltration that goes up into the attic. So these areas need to be sealed. You may be asking yourself, well, how much leakage is it? Well, Owens Corning did some pretty detailed studies and come up with some fairly good real world results. This shows that about 0.3 to 0.7 of a CFM per linear foot is, you know, pretty common. And if you add all that up, In a typical home, that's anywhere between 0.3 and 1.6 air changes an hour. Now, remember, most parts of the United States, we can't have homes that leak more than 3 air changes an hour. So air sealing these areas are really important. Other approaches in new construction, for example, we can use gaskets like you see on the left-hand side. These are simply foam gasket that you put around all the interior and exterior wall plates, or you can buy products today like come out of a can that are pretty durable and easy to use as well. So there's lots of options to seal these areas, but these are areas that I see very few builders focusing on. And that's why oftentimes they have trouble meeting this 3 air changes an hour, because they're overlooking some of these really obvious areas. So if we go back to my attic, you can see that I air sealed every nook and cranny, all the perimeter areas, stairways. For example, here you can see the image on the left is the stairway area for a curved staircase. You can see where all the foam's out in the image on the right, but this is the kind of diligent sealing you need to do. And most areas of the country now require, hurricane clips, and these can actually shim out the drywall about, 3/16 to 1/4 of an inch, and that's along the entire perimeter of the structure. So that can be a real leakage point there as well. So gaskets are helpful, but what we do, instead of using these hurricane clips, we like using these SD fasteners. These are long tempered screws that go from the stud into the plates, into the truss, or simply from the plate into the truss for hold downs. And they're about 30% stronger than typical clips. Then plumbing walls, anywhere we have an opening seal. And around ducts, for example, they found that this is about almost 7 CFM per boot. Now, this is obviously retrofitting it from above, but from below, it's easy to fix that too during construction. You see the image on the right, you can see there where the arrow's at that, that's totally not sealed. And you look at the image on the left, you can see that they ran some foam sealant where that boot intersects the framing. And then when it's all said and done, basically you want to air seal everything, and you want to make sure that we never foam over light fixtures, because light fixtures have thermal overloads and your lights will turn on and off. So we be careful about that. But you may be wondering, what did all this air sealing do for my situation? Like I said, 4,460 CFM before air sealing, and get this, just air sealing the attic alone dropped the air infiltration rate to 2180. So I cut the air infiltration rate of my whole 2-story house in half. And this is a home that's on a crawl space and standard walls that you really couldn't do much to air seal, but just air sealing the attic cut the infiltration rate in the entire structure in half. So in new construction, most cost-effective place to focus on certainly is the attic. Not that we don't focus on these other areas, as I'll show you, but certainly it's really critical to focus on the attic. Can lights can easily be, 9, 10 CFM, per can light. And today it just doesn't make sense to use can lights in homes. I mean, they're leaky. It's much better to use LED type products. They're, gasketed. They're much more easy to air seal. They're more efficient. And most importantly, they don't put big holes in the building envelope that you can't air seal very effectively. Drop ceilings is another area that I see lots of mistakes being made, where we have lack of insulation oftentimes and this area is not sealed. So how do you deal with that? Well, they make great products for this. I mean, there's thermoply, which is like a cardboard structural sheathing that's really easy to work with. You can cut that with a box knife, caulk and seal these in place like you see in these illustrations. We see a lot of coppered ceilings in today's construction, and oftentimes these drop ceilings like this don't have any air barrier on the top of it. So here you can see that this is the case where they used OSB for the entire drop ceiling area, and then they caulked and sealed all that with foam insulation. And these are the kind of things that you really need to do to get the performance that you're looking for. Here's an example of using cardboard sheathing as an air barrier, but as you can see here, it was poorly installed and they didn't come back and air seal. And it's so poorly installed that it would be difficult to air seal that. So again, proper inspection and due diligence along the way is really critical to overall performance. Soffits around kitchens and so forth, oftentimes they're not air sealed very well and they leak like sieves. So a simple, easy thing to do is simply put up your drywall a little ahead of time there and then attach your soffits to that. And that reduces a lot of the air infiltration that takes place around the perimeter, and comfort issues too. Oftentimes these soffits have can lights in them and they leak, and people feel those drafts and stuff when they're at their kitchen sink. And so bottom line is, this is a simple solution. Also, paying attention to the framing schedule and looking what we need to do during the framing process. Like, for example, here you can see where the red arrow's at. This whole area behind this bump out here is not air sealed. And here's another example of another day, another job site where you see this fiberglass insulation's exposed. Now, fiberglass is a fine insulator, but it's not a very good air barrier. And as air flows through the fiberglass, as you'll see later, it has a big impact on the insulation's performance in terms of effective R value. You'll be surprised at some of the graphs I'm going to show you in a little while. But in any event, this air barrier needed to be installed before the framing was done. And otherwise, when these insulations left open, this is a 30-year-old house that had some significant comfort issues. And you can see all these black marks on the insulation. That's not mold. That is strictly dirt. And that dirt is there because of air infiltration and exfiltration out of the building envelope. So this is why the code's now requiring air barrier materials over all exposed insulation, unless that insulation is spray foam. But again, fiberglass is a good insulator, but you have to cover it up with an air barrier. And what that kind of looks like in the real world, properly done, you can see here that they put up the sheeting, and it also makes good shear wall as well before those mono trusses were framed on the garage. So again, paying attention to the little details each step of the way is really critical to getting the kind of performance that we want. And it doesn't have to be fancy. I mean, here's an example of where they wrapped the building before they built on the front porch. And this is a fine air barrier, works fine. There's another example of a knee wall where they used this product called Thermoply. It's a structural cardboard sheething that goes over the insulation, and this can easily be air sealed so that we don't have air infiltration and poor performance at knee wall areas in attic areas. Another area that I see lots of mistakes being made is when we start dealing with fireplaces and plumbing penetrations. For example, here, this fireplace chimney goes up and the flue exits out through a roof, through the wall over the garage. But if you look at this carefully, you can see that the hole that's there is, almost 16 inches wide and over 1.5 feet tall. That's a big hole. And if you're trying to get to 3 air changes an hour, you're not going to get there, with construction like this. Here's another typical example that I see a lot in job sites is where we've cut a huge hole for a flue for a fireplace. Pretty easy to come back with sheet metal, fire resistant caulk, and caulk and seal these so that we don't have these big problems. I mean, if you go back and look at this hole, warm air is more buoyant than cold air, so it rises, and it rises a lot and fast. And so the chimney effect has a huge impact on overall building performance. And that's a big hole. This is probably something more common that I see is where they'll put if you look at this image on the right and look where the red arrow is at, you can see that they put a non-combustible thimble where this B vent goes through the ceiling here. And you'll notice that there's about 1.5 inch gap all the way around the perimeter of that. And that ends up being a pretty good size hole. So the picture on the right is a much more effective way, to seal these types of penetrations. And if you use direct vent appliances, so that really solves those problems as well, because we're not running these flues all the way up through the structure. So anytime that you buy a furnace that's more than 90% efficient, it's going to be a direct vent furnace that you can vent directly out the side wall of a home. Same way with gas water heaters as well. There may be many products that you can vent right out through the side walls of your basement or wherever you decide to put your equipment. Paying attention to the details before drywall is installed, inspecting and looking for these common defects that are often overlooked, really important. This is where it's done right. Anytime that we start running ductwork from one location to another, we got to ask ourselves, when these people come in and they cut these holes, is anybody following back through to make sure that we air seal? This is a really common thing that I see a lot when we run ductwork up into attics. So they'll make a cavity for the ductwork, but then nobody puts a good air barrier system in to air seal this. And here's an example of, we have 1, 2, 3, 4, 5 ducts. This is an opening that goes up in the attic that is roughly 2 feet by 10 feet. That's a big hole. And again, you're not going to get the kind of performance by not air sealing these locations. Ideally, what we should be doing is not putting ductwork or space conditioning equipment in attics. Ideally, if we can keep this inside the conditioned space, we'll be light years ahead in terms of building performance. So let's talk a little bit about what typically happens in attics, particularly during the cooling season. When we have ductworks in the attics get upwards of 130, 140 degrees. So let's just do a little example to show you how much of a penalty it is. If I have a 2,000 square foot home, and typically, if you look at the amount of ductwork that is in a typical attic, it ends up being about 40% of the surface area of the attic. This is studies that we learned when doing some work for the California Energy Commission. So if I have only R4 ductwork on my installation and I've got a 140-degree attic, that ends up being 16,000 BTUs per hour, or almost 1.3 tons of air conditioning. So if I have a 3-ton unit in my home, or a 4-ton unit, that's a third to 25% my whole design cooling load that is being wasted simply because of having ductwork up in my attic. So anything we can do to pull this ductwork out of our attic is important. Sealed attics are great for this. Typically, when you look at a non-vented or sealed attic, their temperatures are within 5 degrees of the conditioned space temperature. And so we don't have these huge energy penalties associated with that. Also, we want to pay close attention about where we air seal. Here, for example, the tradesperson just didn't understand the concept of what a building enclosure is. They air sealed the stud before the exterior wall, where they should have, air sealed this, where we're over here, where we see the wiring going through this wall here into a garage. Another areas that we often overlook are air barriers over enclosed spaces, like behind tubs. Here, they did a good job on the air barrier here. They'll still have to come back and caulk and seal that. As you can see, they did caulk and seal it, but then the plumber comes along and then he cuts a pretty good size hole in the air barrier there. And so unfortunately, that's not going to be good for the building envelope, right? Also, behind fireplaces, we don't want to leave any exposed insulation. So here they came back and covered this up with drywall instead of just being left exposed like you see here. Don't forget the plates. Now, oftentimes everybody seals where that plate meets the subfloor or the slab. But once you look at these numbers here, if you look at the where we typically seal in the upper image, and then you see that's basically 0.1 CFM per linear foot. But then if you look at the lower image on the right, you can see that there's almost 6 times as much air leakage over the top of that plate at the drywall. So the image on the left is where you see air leakage, and the thermographic image, obviously, you see air leakage at this location. So what I recommend is that you seal both where the OSB meets the plate and also where the plate meets the subfloor. So you eliminate this air infiltration at these locations. Really important. And then oftentimes where we have garage walls intersect with the house, we don't have a continuous plate there because of the difference in floor elevations. So we want to make sure we come back and block those areas. One area that's really easy to do is just simply wrap that living space to garage wall connection and make sure that all the joints are taped and everything's adequately sealed. So this is an area that's often forgotten and really makes it difficult to meet that 3 air changes per hour. Don't forget between floors. If we add up on a typical 2,000 square foot house, the amount of joints and cracks and gaps at all these plate locations and band joist areas, it ends up being about a half a mile of cracks and gaps. So it's really important that we air seal these areas. And one of the simplest ways to do that is simply with spray foam. You can use kits and cans. That solves any issues around irregularities around placing fiberglass insulation that oftentimes is poorly placed. Don't forget cantilevers. They can be big leakers. Look at all the daylight we see at each one of these floor joists. When we use I-joists, they're great materials for engineered lumber, but when we try to block around them, oftentimes we forget to air seal these locations, and that ends up being some pretty big holes. So we want to make sure that we air seal and insulate properly in cantilevered areas. And that typically is easily done with spray foam and seals those areas and insulate pretty well. Don't forget, obviously, between crawl spaces and basements and plumbing penetrations, easy to pick about any material you want as an air barrier and then caulk and seal around that. And slabs too. It's really important that we air seal all the penetrations below the slabs, because if we have ductwork up in an attic, for example, and a slab for home and that duct leaks, it's going to put the home under negative pressure. And if we don't air seal those areas, we're going to be pulling air from underneath that slab into the home. And oftentimes that's where these moldy, musty smells come from. So it's really important to air seal all the penetrations in slabs as well. And then we oftentimes people say, well, if I build a house too tight, I'm going to have moisture problems. You know, the house needs to breathe. No, houses don't need to breathe. Houses need to dry. And what I found in my 30 years of field investigations of building problems is that leaky homes have way more problems in terms of moisture problems and mold problems than do tighter homes. So here's a great example of a home I looked at in the Oregon area. This is along the coast there. It wasn't even that cold. I had a great vapor barrier installed. I cut it loose, but the homeowner was an HVAC contractor. So he put an 8-inch diameter supply duct and ran it from the outside of his home into the returner side of his furnace. So every time his home operated, it put the home under a positive pressure. We also had kids with asthma, so we had 3 vaporizers running 24 hours a day, 7 days a week. And so that moisture load just forced that moisture laden air out through all the cracks and gaps, and every one of the stud cavities had mold growing in it like this. And so that was a pretty expensive callback. But the bottom line is, if you stop the airflow, you stop the moisture. You know, so it's really important to do this air sealing, not just for energy efficiency, but it also stops the transport of moisture laden air into places that we could have condensation or even dampening the building materials to the point where they create problems. So with all this being said, you know, it's really important that we figure out a way to ventilate homes efficiently. So, you know, this is why we want to use controlled fresh air ventilation systems with energy recovery. So if we breathe about 3,000 gallons of air every day, and this natural ventilation that we hope that ventilates the home is really just accidental. And so what happens in the months in the winter, so when the temperature differences are the greatest or the wind speeds are the greatest, our homes are grossly overventilated. And then in the swing months and the months where we don't have big temperature differences, our homes are underventilated. And so we want to have just the right amount of ventilation. And so this is why it's really important that we use energy recovery. And the cool thing is, and we have great new technologies that are going to be on the market this year. This is one system that has a sensor that can measure CO2. It can measure PM 2.5. Those are particles less than 2.5 microns that can bridge the gap between your bloodstream and lung tissue, lead to cardiovascular disease, that type of thing. It can measure VOC and temperature and humidity, and it can automatically control your entire system to ventilate your homes as needed. So in other words, for the first time, we'll be able to actually monitor indoor air quality in your home, and these systems will automatically control your ventilation system to bring in the right amount of fresh air. So we're not overventilating and we're not underventilating. And they're all controlled by an app on your phone. They have sensors like here, these switches that also will tell you whether or not you have good indoor air quality or poor indoor air quality. So these systems are exciting, and they're going to be on the market this year. So with that in mind, next up, Gordon's going to talk about the importance of ventilation, and I'm going to hand this back to Joel.
Well, that was fun, Joel, answering those questions. And Steve, I really appreciated your comments early on. That whole concept, you can imagine, both you and I have been hearing for 35 years. We build them too tight and walls have to breathe. And I really liked how you said it, walls need to dry. But in fact, houses do need to be ventilated. And whether we call that breathe or not, and we're going to talk about ventilation. I'm going to put it in the context of indoor air quality and ventilation. I want to talk just kind of 3 little topics in the next 15 minutes or so. A little bit of a history of indoor air quality and ventilation and how codes and standards view that. Second, a little bit on how to choose the right ventilation system for your high performance home. And third, some of the details so that you can be successful with ventilation is important. And I just want to point out to you, we've known about ventilation a long time. In addition to all of the great things that Benjamin Franklin did, he was also known as an indoor air quality specialist. He worked with churches and schools and office buildings, and he talked about this phrase here that air's unwholesome, that's often breathed and not changed. And back in his day, how did he ventilate? Well, he didn't have energy recovery ventilators. He had windows, and he would help people understand that they needed needed to open windows and leave them open. So we used to ventilate not through holes in electrical outlets, not through holes in can lights or behind fireplaces, but by using windows. Indeed, I always ask people, Steve, when they say to me, you have to build you want to make a house actually looser, not too tight, I always ask them, well, exactly what is the right number of holes in the walls or attics of somebody's house? And of course, their answer is there's no right amount. We want houses to be as tight as possible, but we also need them to be ventilated. We used to ventilate with windows, and now we don't. And so when we talk about good air, what exactly is it? How would we describe it? And one of the things that we always point to is it should be as good and as clean as outdoor air. And you think, well, is outdoor air good? Well, I'll come back to that in just a second. But more importantly, or as importantly, you want to use your nose. Has no odors. Our nose is a wonderful scientific tool. The problem is it's connected to a very lazy brain. So one of the values you bring as a contractor or as a consultant is that you walk into a house and you actually smell new odors that homeowners have forgotten about. So really, we want the absence of smell. We don't want lavender fresh or wintergreen coming through those plugins. We want no smells in our houses whatsoever. And of course, measure fewer pollutants. And Steve, you had mentioned that we now have the ability to actually measure in real time and make control strategies. We've actually had the ability to measure pollutants. We've never had the ability to do much about it. We want to actually turn something on, filter it out, or vent it out, ventilate it, exhaust it out is what we really want to get to. And ultimately, meaning healthier to breathe. The healthiest possible air for you and your family is what we're looking for. Sometimes we need to remind ourselves that indoor air quality complaints are actually temperature and humidity complaints. That's interesting. So we have to have the right temperature, the right humidity, and then making sure that we have fresh, clean air. Now let's go back to that idea of outdoor air. Is it in fact clean and fresh? Well, it turns out the Clean Air Act of the 70s did an amazing job. It reduced smog alert days by over 80% in every major city in the country. And it turns out that inside air is actually worse than outside air. That is, when you think about it, where did the air that's currently your house come from? Well, it came from outside. Then you cooked in it, lived in it, breathed in it, showered in it. You actually made the air quality worse. So as bad as the outside air might be, you're actually making it worse when you live inside. So we still need to ventilate. Now, there are some days, of course, where we don't want to be bringing in that outside air. But in general, we want to imagine bringing in outside air to solve or help dilute indoor air quality problems inside a house. That said, so what has changed? People often say, well, is air quality worse than it used to be in houses? And the answer is, it certainly is. It has partly to do, as Steve mentioned, partly to do with making houses tighter, but that's not the most important part. We have started adding more chemicals to our houses. You think about carpets and furnishing and furnishings. You think about air conditioning. We used to have our windows open reliably in the 50s and the 60s. Our windows were open all summer long, and now we're closed up pretty much all year round. What's important to understand is we're spending in the middle there some more time indoors than ever before. And even during this time of COVID, imagining home offices, homeschooling, we have more and more issues associated with people spending more time indoors. And most importantly, we use windows less. I say this all the time. I remember as a kid, mom coming in, opening my window at night, saying, we'll leave your window open an inch, Gord. We'll leave your brother's window open an inch. That'll create a nice cross draft. And now people spend hours and hours a day with windows closed. Why? Because of noise, dust, security issues. We, generally speaking, people don't want to leave their windows open. And then on the far right, of course, we have changed the products that we live with, that we use. More personal hygiene products, more chemicals, more furniture and furnishings that we have to think about and worry about. So lifestyles have changed. The good news is we know the priorities. We know how to solve indoor air quality problems. That is, the EPA and others have created a really nice guideline. First and foremost, you would get rid of pollutants, remove pollutants from the house. Now, I always like to say, if Johnny's allergic to the dog, get rid of, Well, you might say, Johnny, well, we love the dog, we love Johnny, we can't get rid of either. Okay, fair enough. In general, though, as builders, as designers, as architects, as contractors, make sure you're not using products that off-gas. Use products that don't smell. Use your nose. Remove pollutants. But if I can't remove them, Johnny and the dog, then the second best strategy is what's called a seal strategy. Steve mentioned isolate the house from the garage. Really, really important. There's pollutants in that garage. Reduce pollutants from attics. That's what Steve's concern, from attics into houses, because the air in attics isn't necessarily good, especially, Steve, as you have bat problems up there. What about crawl spaces? So we need to think about seal strategies is the next most important. Third on the list, noticed, is ventilation. And fourth is filtration. Now, I'm not saying filtration isn't important. What I'm saying to you is ventilation is more important than filtration. Ventilation is third on the list of things to do. Remove what you can, seal or isolate what you can, but ultimately start ventilating houses, controlled, intentional ventilation is what we're looking for. And the code actually helps you with this. Steve mentioned that, in fact, the new codes require you to do air tightness testing as of 2012, 2015 code. Houses in the south have to be under 5 air changes. Houses in the north have to be under 3 air changes. And the IRC is saying if your house is under 5 air changes, then in fact, you do need to put in a whole house ventilation system. That's interesting. And when you think about the definition of indoor air quality, who is defining what this is? Well, it turns out there's a great standard for this. ASHRAE, American Society of Heating, Refrigeration, Air Conditioning Engineers, allows you or gives you a standard 62.2, that describes exactly how much ventilation you should be putting in houses to make sure that the majority of occupants express no dissatisfaction with that air quality. Now, it's not saying it's the be all and end all. It doesn't handle smokers. It doesn't handle unvented combustion appliances. But as a general rule, ASHRAE 62.2 gives you really good guidelines as to how much ventilation you really need in your houses. Good to know that we have that there. And from a perspective of a definition, when we say ventilation, what exactly do we mean? It's a means of providing fresh air. Now, you could argue, is the air outside fresh? Steve mentioned PM 2.5, particulates, smog, those fine dust particulates. The good news is we have the ability to filter those. If we knew where the air was coming in our houses, that is, if we had control over the air was coming in, unlike a leaky house where we have no control, with our ventilation system, if we know where the air is coming in, we can filter it and take out those fine particles and turn what might be the pollutants in outside air into something that's healthier and fresh. And the key phrase here out of today's little segment is to understand this. All builders have the responsibility to create the capacity for continuous mechanical ventilation. That's a key word, capacity for continuous mechanical ventilation. That is, ultimately, it's your homeowner's house. If they don't want to run their ventilation system, that's up to them. There's no ventilation police. But you as a builder, and whether you're in Florida or Phoenix or Texas or the Northwest or Hawaii for that matter, you have the requirement to provide a capacity for continuous mechanical ventilation. And some days you might say, I don't want to bring in that hot humid. Sorry, you got to get over it. You have to provide that capacity, and I'll show you the ventilation rates that you want to work on. And it helps you control moisture, it helps remove common pollutants, and it helps ensure good air quality for the occupants, the healthiest possible air for you and your family. And so the good news is ASHRAE 62.2, the version 2010 that you see here, describes exactly how much, allows you to calculate exactly how much ventilation you need in any particular house. And it's based on the number of occupants and the size of the home. Notice the formula in the middle of the page. CFM, cubic feet per minute, the amount of fresh air that you need, capacity you need, is equal to the number of bedrooms plus 1 times a factor of 7.5 CFM. And then you add to that 0.01 per square foot of house times the square footage. And so that gives you a ventilation rate. Simpler yet is the table. If I said to you, I live in a 4-bedroom house built in 1992, it's 1.5 air changes just under, pretty tight for the time that was built back then, but it's a 4-bedroom house, it's 2,500 square feet. If you look at the chart, it's a pretty simple calculation, 75 cubic feet per minute. What's powerful to understand is I've lived in that house, 3 kids, a home office. I've measured air quality. though I live in a really tight house, I have really good air quality because I have the capacity for continuous mechanical ventilation. I have control over the air quality in my house. You'll notice I mentioned it's a multiplier of 0.01 per square foot of house. Of interest, perhaps, is ASHRAE changed their ventilation rates in 2013. They actually increased that adder to 0.03. Here's why. In the past, the old rate assumed the house was leaking some amount, and they didn't. Now we don't know if a house is leaking or not, so they've actually shown a different adder. Now, you're allowed to go back and recalculate and say, hey, my house actually leaks a little bit, so I don't have to put in this much. But I just want you to have this sense that as simple as 75 to 120 CFM of air is all you need. When you have that amount of air, you can go ahead and make a house as tight as you want. So very simple formula. All of you can think about today, right now, take a screenshot and think about your own house. How much ventilation should you and your family be receiving on a continuous basis? And if you're not, when you go home, as you think about the end of this session, then think about what could I do in my house to improve the air quality. And there's a little example of a 4-bedroom house at 2,500 square feet, basically my house, 120 CFM. And now you can go ahead and make a house as tight as you want, go all those techniques that Steve just showed you, you'd be in good shape. And then in addition to that, we do want some source control. The ASHRAE standard would say, as a minimum, we would like 100 CFM out of a kitchen if it's running intermittently. If it's running continuously, say 60 CFM. Your partner in the ventilation industry, the Home Ventilating Institute, which represents all the manufacturers of bath fans, range hoods, HRVs, and ERVs, they actually would say, go a little further than that and use a per lineal foot of range. So per lineal foot of range, you'd have at least 100 CFM. So a classic 30-inch range hood, 30-inch range would need 250 CFM of air. Pretty powerful. And then if you're using the gas range down at the very bottom, we need even a little more air. It's a 100 CFM per 10,000 BTUs of burner. That's more of a heat rise issue. We don't want the heat from the gas flame overheating the ductwork, but you get a sense that we need two things: capacity for continuous fresh air, and then we need to think about source control at kitchens and bathrooms, because those are areas of big pollutants. And in terms of then determining the right system for your house, it's thinking about determining the required airflow. We just did that, got that one done. Next, we'd want to select the ventilation strategy. Exactly what kind are we going to put in? Third, if we are going to go to balanced or with energy recovery, should we be using heat recovery or energy recovery? Then we want to think about how are we going to get this installed? Think about the ductwork, the duct layout, what kinds of systems do we want? And then lastly, think about the efficiency and the control strategy that you're going to use for that ventilation system. And when we think about the type of ventilation, you kind of have three choices. You have exhaust ventilation, you have supply ventilation, or you have balance. Exhaust meaning a bathroom fan taking air out and somewhere air leaking in, or a duct bringing air in, much like that house in, I think it was Portland you mentioned, Steve, bringing air in and where is it leaking out? And one thing you need to know is the building science community has pretty much settled out and said, you know what, just get to balanced ventilation. Air in equals air out. It's best for the building, it's best for the occupants, it's best for control of indoor air quality. Balanced ventilation. Of course, I'm going to advocate in high performance for energy recovery ventilation, but you should be moving yourself towards balance. Make a note, if you're at exhaust or supply only ventilation, in the next 1 to 2 years, you should be switching to balanced ventilation with energy recovery if you're going to call yourself a high performance home builder. So choose balanced. Air in equals air out, that consistent flow. It gives you much simpler control strategies, all in one box, 2 fans in a box. And it gives you that opportunity for temperature and moisture control of that fresh air coming in. So it's no longer just leaking in unknown locations. You now have the ability to heat, cool, ventilate it, control it from a moisture perspective. And ERVs, for example, are the unit of choice, I would say, in the vast majority of places in North America. You'd like to be using ERV technology or energy recovery technology. They recover 55 to 75% of the temperature difference between the inside airstream and the outside airstream, and they recover 50 to 60% of the moisture difference. Let's just do a quick example. You know, if it's 90 degrees outside and 70 degrees inside, that's a temperature difference of 20 degrees. At 60% recovery efficiency, 60% of 20 degrees is 12. So instead of the air coming in at 90, it's coming through the energy recovery core, and it's coming to you at 78 degrees. Now that's still warmer than the 70, but it's way cooler than the 90. It reduces your cooling loads. It reduces in the same way your moisture loads. That's what energy recovery ventilation is doing for you. Here's a little animation of how that runs. So this is showing a southern application ventilation system located in a ceiling. So it's you'll see it in a second here, but showing that device located in the attic. It's pulling fresh air from a location like a gable end, not off the roof itself, say off a gable end or off a soffit, bringing that air into the house, recovering or removing some of the heat, removing some of the moisture, and in this case, dumping it into the air handler return. Simultaneously, it's taking air from the house, maybe from the bathroom instead of a bathroom fan, putting in the ERV vent and passing that air through the ERV, recovering the energy from that and delivering that air to the outside. And here you see the box mounted in the ceiling space and just showing the magic of 2 fans in the box. That's all it really is in this energy recovery core, a flat plate heat exchange made out of a media that transfers both temperature differences and moisture differences and minimizes, it's not a dehumidifier, but it minimizes the loads associated with moisture and temperature in this house. Get the idea? Pretty simple device, and draws in terms of wattage 20 to 60 watts. So it's like a light bulb being left on. In terms of cost, people say, is it going to cost a lot? You know, the best of the ERVs these days are 20 to 60 watts for the ventilation that they're bringing into a house. And people do say, well, is this going to increase my loads? Well, I want you to imagine that 75 CFM ventilation. Remember that 4-bedroom house, 75 CFM ventilation? Let's go to Minnesota and let's say it's, 20 degrees Fahrenheit outside. That's not even a very cold day in Minnesota. That ventilation adds in the order of 1,650 BTUs. It's not going to change your furnace size. Let's go over to Phoenix at 100 degrees Fahrenheit. That ventilation is going to add about 3,500 BTUs, about a third of a ton, if you will. And more importantly, in the Southeast, the Florida market, where it's hot and humid, that's going to add about 4,500 BTUs. The key is about 2/3 of that is latent load, the moisture that's in that air. The good news is those loads aren't that huge. This is 75 CFM of ventilation running continuously. And more importantly, if you do it through an ERV, you can reduce that by as much as 70%. Why? Because the ERVs are 70% efficient. So imagine using ERVs and what the impact would be on the loads. And it's really not that great a load. And so then there are high efficiency ERVs that have ECM motors that have efficiencies up to 70 or 80%, even this one's showing 88%. Some of them have HEPA filtration built into them. So those fine particulates from outside are first meeting a high efficiency filter so that you're not getting those pollutants from outdoors. So some really nice technologies out there these days. A couple of key hints: make sure you're verifying the flows. Remember you said you want 75 CFM? I would like your HVAC contractor to commission and measure. And most units on the market actually have built into them flow measuring equipment. Use a very simple gauge, the same gauge that they use for doing blower door testing, and it will tell you exactly how much flow you're getting. That way, when you leave the house for the client, you know that you've given them the healthiest possible air for them and their family. And there are lots of options out there. You guys would know the bathroom fan and range hood market, tons of options if you want to do exhaust only, but you're going to go to balance. Or by all means, go to supply only ventilation. There's some good materials on the market as well. But lastly, think about energy recovery ventilation. And the good news is there's 3 or 4 really good, solid North American manufacturers that are building equipment with, dozens of different models. Some are top port, side port, to give you duct configurations that you can install pretty much anywhere, in a ceiling space, in a closet, down in a basement next to the furnace. There's really no excuse for not looking at balanced ventilation with energy recovery in these days. And to finish up on this particular slide, think about the win-win-win of ventilation. For homeowners, it means fresh, healthy environments, clean, pleasant smelling air. For HVAC contractors, it allows you to reduce moisture load specifically, but also your heating and cooling loads. So really powerful to optimize the loads of heating and cooling systems. And of course, for builders, it gives you options and choices to add to your value proposition to homeowners for any particular house, and it gives you better, more cost-effective energy scores. So these products are recognized, energy recovery products are recognized as part of a HERS score. So very powerful that we have these choices available to us in ventilation. Now you can go ahead and make a house tight, as Steve mentioned, with making sure the house still has the ability to dry, and more importantly, homeowners have the healthiest possible air for they and their families. Joel, back to you. Any questions that have come up on the chat?
Well, Gord, that was great information. I can't emphasize enough how much I agree with you that indoor air quality is such an important part of our lives these days, particularly when we're spending almost 24/7 in our homes. And so great information. Well, I'd like to move into the third part of our presentation and kind of talk about some of the other factors that really do affect home performance. And when we think about insulation, we tend to think of it only in terms of its R value, but we don't really think of it in terms of its effective R value. And so this was a study that was done by Holometrics way back in the 90s. And what they determined is that as air flows through insulation, it scavenges away heat. And so this chart here kind of says it all about how important it is to have proper air sealing in order to make your insulation work up to its full potential. So we start up here with our typical R14 wall, and then we look at our wind speed across the bottom. And even with a 7-8 mile an hour wind, the R value of that insulation drops to about 8. So having a good air barrier system, installing the insulation correctly is really critical to its overall performance. Our fibrous insulation that we use today is pretty economical, and so it ends up being the most popular choice. Now, the image on the right here was a home that I looked at a number of years ago, and I put a blower door in this house, and I depressurized the house to 50 pascals, and each of the wall cavities that you see was insulated from the top all the way down to the floor. The cavities were completely full. But if you look at the thermographic image here, you can see that the temperature drops off dramatically when we start getting close to where the air infiltration is. You might recall from my other slides how much air infiltration leaks at those plate line areas and around the drywall and over the top of the plate. And this is proof perfect that wind washing does impact the overall performance of insulation. In fact, this insulation works by its ability to trap air. So when you look at like fiberglass insulation, for example, it's not the fiberglass that makes the insulation, it's the air spaces between the strands of the fiberglass that create the insulation. So an insulation's ability to insulate is directly proportional to its ability to trap air. So if we install the insulation in ways that it's compressed and not fully lofted, then we're eliminating some of those air spaces that impact the overall performance of the insulation. So for example, here you can see that where it's compressed, it might be R8, where it's fully lofted, it might be R13. So the critical thing here is that we recognize that how you install the insulation is just as important as how much insulation that you put in. So this is an example of a colleague of mine, Rick Chitwood. He built a knee wall and put some heat lamps behind it. And so one of these has an R11 insulation bat perfectly installed, and the other is an R19 bat typically installed. And so when you look at what that looks like in the real world, I can put in an R11 bat perfectly installed and actually have it perform better than an R19 bat, like in this case, because of the way it's compressed and the gaps around the insulation basically end up making that insulation about 3.5 R value for the whole system. So that's not good. So bottom line is we really want to make sure the insulation is fully lofted, fully fills the cavities, no gaps, cracks. It's in full alignment with all of its air barriers. So what does that really mean? It means that the insulation, there are no voids. The insulation is in contact with the bottom plate, the upper plate. It's in contact with both sides of the studs, in contact with the exterior sheathing, and in contact with the interior drywall. And so this is kind of what that would look like. And if you're looking as a ResNet energy rater, they have what they call ResNet grade 1. That means the insulation is installed perfectly with no gaps, cracks, so forth. Here's an example of what looks to be a really good install, but look carefully at that and tell me if you can see why this would not be a good installation. Well, in this case, we have 2x6 walls, but they only put in R13 batt insulation. So there's a 2-inch gap between where the drywall is and where the face of the insulation. And so if you're going to spend all that money on wood framing for 2x6s, you want to make sure you totally fill that cavity. Also, thermal bridging is a big factor today because we tend to overframe homes. When you look at the typical framing factors of a house, they're typically about 25%. So that means that if I have 1,000 square feet of windowless wall, 250 square feet of that wall is the R value of a 2x4 stud, which is about 4.35. So the framing factor has a huge impact on the overall performance of the walls. And that's why all the codes are moving more towards exterior insulation. Now here's typical framing. This is probably close to 30% framing factor. Look at all this wood in this wall. I have builder clients that are actually doing CAD drawings of every wall in the home to show exactly where every stick goes. And they are saving about $1,000 a house, about $1,000 a house. So and in today's prices, even greater than that. So, if you were looking for some advice on advanced framing, there's a great guidebook put out by the American Panel Association. You simply go to apawood.org and you can download this advanced framing guide. And it really walks you through some of the common sense things that we can do to trim out some of the lumber out of homes that will increase our overall R value of the wall and also not impact overall performance. I mentioned that we were consulting on these zero energy homes out in the Central Valley, and I just thought I'd show you kind of some of the things that we're doing here. You'll notice that this exterior wall, there are no headers over the windows. But if you look up and take a good look at this truss, you'll find out it's not your typical just in-wall nailer truss. What we did was we did a load-bearing basic W truss, and then we added the nailers so they could attach, in this case, cement board siding, and that allowed us to eliminate the headers over the windows. You also notice that we're using, this engineered lumber for our single top plates. These are single story homes, so we don't really need to have double top plates. And then you also notice that we don't have a lot of trimmers around our doors and windows. We haven't had any drywall callbacks or any issues associated with that. We simply make the windows, design them so they fit within our 2 foot on center 24-inch module. And we're able to get these framing factors down to about 11 or 12%. Now, what does that do for us when we think about increasing the overall performance of the wall? We can simply add some exterior insulation. And so if you look at your typical 2x4 wall and take into account the framing for an R13 wall, the actual R value drops to about 10.7. But if I add even 1 inch of, say, styrofoam, for example, at an R value of 5 per inch, that wall goes from 10.7 up to 16. So that's a big improvement in terms of overall efficiency. You may be thinking, well, hey, lumber is so expensive. Why don't I think about using steel? Remember, steel is much more conductive, 1,000 times more conductive than, say, a wood stud. And so that has a big impact on performance. And so you say, well, Steve, how much is it? Well, let's just take a look at this chart. And this is the impact of thermal bridging through steel studs. If I have a 2x6 wall cavity and I'm using an R21 batt with a steel framed wall, the R value of that wall, get this, drops to 7.4. So that's almost a third of its original R value, just because the added conductivity of the steel studs. Now, one of the things that we're doing in the zero net energy homes is we simply put our foam sheathing underneath the OSB. We had an engineer do the calculations for this part of California, and we didn't have big seismic issues. So we could essentially just basically sandwich the foam behind the OSB. That way we could do our building wrap and put in our windows and doors just like we have for the last 100 years. But again, you would want to get this checked out by your local engineer to make sure that works in your particular market. Now, as I mentioned earlier, the codes are really moving towards exterior insulation, because of these thermal bridging issues. And for example, California instituted a code in 2016 for their high performance walls requirement, and the prescriptive part of the code basically requires exterior insulation. And the codes throughout the rest of the United States are moving in that direction as well. In fact, the 2021 code, if it gets adopted, you'll be required to use continuous insulation in climate zones 4 and above. But what happens when we start putting an impermeable insulation like foam insulation over wood sheathing? Well, now, as you can see here, we have a different set of problems because, our wall systems with foam sheathing over the top of it is not exactly going to be have very great capacity to dry. So if we do get water between the foam and the OSB, we've got some real problems on our hands. So not that we shouldn't do continuous insulation, it just means that we're going to have to be a lot more diligent about how we employ our weatherization practices and how we integrate our flashing and how we integrate our weather barrier with these type of construction techniques. And Gord's going to go into a lot of detail about how to do that in a little bit. Now, other thing that's important to note that our building materials have changed quite a bit in the last 20 years in terms of how they handle moisture. This was a picture of a job site that had some significant water problems behind synthetic stone. And the image on the left is where we have OSB on the top part of the wall system and plywood on the bottom. And so what I want you to note is look how much mold is growing on the OSB, and they're the same circumstances, the same water leaks, and how much better the plywood was capable of handling that. Now, I'm not saying we shouldn't use OSB. I'm not saying that at all. I'm just saying that because the materials we're using today, we got to pay a lot more attention about making sure that these materials stay dry. Also, take a look at the image on the upper right. You can see I saturated two pieces, or one piece of OSB, and the other piece next to it to the right is completely dry. Look how much the saturated piece of OSB on the left, exploded. Every time that lumber gets wet like that, or the OSB gets wet, it expands and contracts and loses a little bit of its shear strength. So it's really critical that we keep these materials dry. And then plywood, if you look at plywood on the left here, saturated versus dry, the piece on the left is completely saturated and the piece on the right is completely dry, and you can see that the plywood didn't grow very much at all. So my point in all this is that OSB is here to stay, no doubt about it, but it is important that we keep it dry. And so there are a few approaches that we take for water managed walls. Number one, we could do barrier walls. Number two, we have what we call drainable walls, which are the most popular today. And number three, we have rain screen walls. And so when we look at a typical barrier wall, that's essentially like the picture you see on the left. All of our water management takes place on the outside of the cladding. And we just hope like heck that all the caulking joints hold and that water doesn't get in between, the exterior cladding material and our wood frame walls. Next is what we consider to be the most popular that we see today, and building codes have required weather resistive barriers behind all cladding surfaces since 2006 or so. But these walls don't rely upon face sealing. They have secondary water barriers to manage the moisture. So any water that does get behind the cladding, we want it to drain and get out as fast as possible. So we have these spaces and we have flashing details that manage that water to get it to the outside of the building envelope. This is nothing new. We've all been doing this a long time, maybe haven't been doing it very well, but now that we're using our wind codes have increased in severity so much, and with regards to requirements, we almost require OSB shear or some type of shear wall materials in almost all the climate zones now. And so when we go through and we add this foam sheathing over the top of that wood sheathing, we've got to really pay attention about how we manage that moisture. So how do we do that? Well, we use rain screens, and rain screens have been around for a long, long time. In fact, the most common rain screen that you're probably familiar with and may not know it's a rain screen is brick veneer. We have that airspace. The code requires typically a 1-inch airspace and weep holes at the bottom so that if any water does get behind the brick, it has some ability to be removed. Well, what rain screens do in modern day is that, we use either these synthetic materials or we could use something as simple as furring strips. So for example, here on the left, we've got these materials that come on a roll and provide that, 3/8 inch space basically behind. And the beauty of rain screens is that the water basically has to jump across that gap in order to create any problems for us. And typically our weather resistant barrier is going to be much more capable of handling that. So the beauty of a rain screen is that it almost eliminates any bulk water from coming in contact with our insulation. And so if you look at the image on the right, this is a mineral fiber exterior insulation, and then furring strips over that, and then our cement board siding. So that creates that, in this case, 3/4 inch airspace that allows for drainage and for drying. So again, if I'm going to be putting foam sheathing over wood-based sheeting, then I want to make sure that I keep that wall system as dry as possible. Now, the last component to a high performance wall system are the windows. And I think windows, oftentimes people don't realize what a huge impact they have on overall building performance. So when you look at this wall, I might have R20 walls, I might have R30 walls, but the real weakest link in this wall system are the windows. And you might be asking yourself, well, how much of an impact does it have? Well, check this chart out. This chart shows the window to wall area ratio, or in other words, or the percent of glazing on the bottom axis. And then on the vertical axis, that is the effective R value of the wall. And so let's just say we're building a passive house or a zero net energy type home where we have really well insulated walls. Let's say like an R30 wall. And let's say that our glazing factor, like typical homes, is 15%. And what does that mean? That means if I got 1,000 square feet of wall and I have a 15% glazing factor, that means 140 or 150% of that wall, 150 square feet of that wall is going to be glass. So let's just take a look at what happens to our R30 wall if we have simply windows with a U factor of 0.5 or an R value of 2. That would be a standard double pane window. The R value of my R30 wall drops from 30 down to 10. Huge, huge impact. Now let's say I have a pretty good window that has a U factor of 0.25 or an R value of 4. My R30 wall now went up to 15. And then if I do something like a triple pane window, like an R6 window, that R value of that wall goes up to 19. So as you can see here, windows are really important in terms of the overall performance of the entire wall. Really critical that we buy windows that have U factors and, ideally of 0.25 or less, and solar heat gain coefficients of 0.25 or less. So when we look at that NFRC label, the U factor is basically how many BTUs per square foot of energy transfers through the glass. And so this window here, for example, has a U factor of 0.3. That would be an R value. If you divide through, a U factor of 0.3 would be an R value of about 0.33. Now, the solar heat gain coefficient is the percentage of heat from the sun that gets through the glass. We use that to measure our summer performance. So this window only lets in 24% of the radiant energy from the sun. Now, the radiant energy from the sun is pretty significant. The sun radiates about 250 BTUs per square foot on a given surface. So that means if I have a sliding glass door that's, let's say 6 by 7, and to make the math easy, we say we have 2 square feet of frame. So that means if I have 40 square feet of glass at 250 BTUs per square foot, that means that over 10,000 BTUs of energy is going to be striking the surface of that, let's say, sliding glass door, which could be, 25% of my total design cooling load, just the heat gain to one sliding glass door. So again, we use the U factor to primarily tell us how well that window is going to perform in the winter, and we use the solar heat gain coefficient to tell us how well that window is going to perform in the summer. Again, I like to see these products be certainly no greater than 0.3 for a U factor. I like windows that are 0.25 and less, and the solar heat gain coefficients of 0.25 and less. And of course, the last number here you see on the bottom is the visible light transmission. That's basically how much light gets through the entire window. And these are total window numbers. They're not the center of glass. It's the frame, the glass, the sash, everything. NFRC numbers are total window numbers. And then the number that's not shown on here is the air infiltration numbers. We want those numbers to, we never want to see a window have more than 0.25 CFM per square foot of air leakage. So with that in mind, I'll turn this back over to Joel, and we'll have Gord go into his next round of the presentation.
Well, thanks, Joel and Steve. Yet again, these new virtual sessions are really cool to see that we're still able to get some interaction and an opportunity to answer questions of folks. And Steve, I want to just reiterate back to what you were saying is this idea of increasing or improving performance of walls. And that's what my next little segment is going to be speaking of, is specifically how do I be successful? What are the methodologies, what are the techniques and strategies that to get that higher performance out of our walls? And in terms of that, I want to go back and focus on the term you first mentioned, which was effective R values. You had said that codes are moving towards insulated sheathing or continuous insulation. That's because they're all focused now on effective R values. We'll chat a bit about that. We will, of course, touch back on the building science connection. I just want to add maybe a little math to what you had talked about, Steve, just to show where the percentage improvements might be, and a couple of options and the execution that you mentioned that kind of like to see how it goes together. I have some animations to show you. So let's start with that. I'm going to focus on, as you already mentioned, the functions of a wall on the thermal control. You already talked about water control and how important that is. I'll touch back on that just a little bit. But from a thermal control perspective, that new focus, jot it down, folks, take a screenshot, effective R values. In our market, the building officials no longer look for the nominal R value in the cavity. They're actually looking for the total performance of that wall. They take into account both the nominal in the cavity, but also the thermal bridges. That is the structural components. What's that doing, whether that's steel or whether that's wood? And I just want to put a finer point on that from Steve's perspective as to where we're headed with that calculation. So much as Steve said, this is a pretty simple chart. Our own website at Construction, you can download this. Every major manufacturer, NEMA has this as well, access to these calculators that'll show you the effective R value. And to Steve's point, you talked about framing percentages and getting to advanced framing. I am in fact showing, remember you said 25% on the top left, 25%, and there is the effective R value of that wall at roughly 10, well, not roughly, exactly 10.54. And you can start to imagine there's three ways to improve the performance of that wall. One, I could take out some of the structure, as Steve mentioned, get to advanced framing. Two, I could think about more cavity insulation. Or three, I could think about continuous insulation. And I'll just show you one quick little piece of that. If I got down to 19%, Steve, I was amazed when you said you got down to 11 or 12, but a pretty typical program of advanced framing, wider stud spacings, properly sized headers, maybe 2 stud corners, you can pretty readily get down to 19%. And notice that little improvement from the 10.54 to 11.35. You're going to say, well, that's less than what R value. Yes, but it's an 8 to 9% improvement at lower cost. Talk about optimizing performance. By getting rid of some of the wood, I improve the performance. In any other industry, if they said, hey, I could improve your performance and lower your cost at the same time, boy, they would have done it yesterday. In our industry, we still struggle a little bit with getting to advanced framing. And the good news is with new panelization that we see happening, factory build, if you will, panel systems, it's never been easier to start describing or prescribing advanced framing techniques into your walls. So that's the first element, would be that idea of advanced framing. The second, though, would be more cavity insulation. I just want to show you the limits, the scientific limits, if you will, of that cavity insulation. If, for example, we took that 2x4 wall, took out the really cost-effective fibrous insulations and replaced it with, say, a high-density spray foam, R7 per inch kind of idea, boy, I could boost the R value in the cavity up to, say, 22.75. But notice it only got you an extra R2. You bought an extra R, what was that, 9, but you only got an extra R2. Why? Because you didn't impact the studs. So showing the need to think about a more synergistic, most holistic approach to managing the overall thermal performance of a wall is what we'd like to get to. So, a pretty typical 2x6 wall, there's a standard R19 in that wall cavity. Now you're up to 14.68. That was actually more cost effective than, say, doing spray foam. And don't get me wrong, I like spray foam. I have it in my own house, not necessarily for the thermal performance, but the sound, the air tightness, and when I use insulated sheathing in the outside, I do get synergistic effects. So don't take this as being against a spray foam product. Think about it as being finding the right place or the right materials as we move forward with this conversation. But that continuous insulation is what I really want to think about just for a second. And if I took that 2x4 wall and added as little as 1 inch, as you mentioned, Steve, now I'm up to 15.54. I got the true value of that insulation on the outside is what we'd like to get to. And if I say R5, some of you are thinking, well, is it foams? Is it fibrous? And the answer is it could be either of those. Lots of choices that you have. But that conversation that Steve mentioned, well, I'm putting a foam plastic insulation, which reduces the drying potential. Some would say it's even a vapor barrier on the outside. And some of them actually are. So we really need to think about the dew point discussion, the conversation. And I have a little animation for you to show here. Imagine this. If I have more moist air that leaks into a cavity in a cold climate, here showing 20 degrees Fahrenheit, more moist air leaking into a cold cavity, I will in fact get condensation. And the more insulation I add, the worse it gets. And there's really 2 ways to solve that. One would be to stop the air leaks, which was the focus of Steve's first session, or in fact to put insulated sheathing on the outside. And indeed, if I put enough insulation on the outside, I've changed the dew point location. I need to warm up the exterior surface enough to avoid condensation. So again, 2 choices. Make the walls more airtight. They learned that in Minnesota 30, 40 years ago. If you don't want condensation in your walls, you got to make them airtight. Steve already mentioned it, another reason to get to airtightness. But the other methodology is adding your insulation on the outside. The more you add insulation on the outside, the warmer that OSB structural sheathing becomes, the less opportunity there is for condensation inside of that wall cavity. And it turns out we kind of know where you're headed with this. That is, if you think about net zero or zero energy by say 2030, 2032, whatever that happens to be, we know in southern climates that what you want to get to is roughly 2x4 with R10 to the outside. And in a northern climate, you'd like to get to 2x6 with R10 on the outside. In virtually all markets, we can do everything we need to do with just putting 2 inch of continuous insulation, 2.5, depending on the type of insulation you're using, R10 to the outside, get you where you need to be. Now, of course, some of you want to go farther than that. I'm okay with that. But when you think about zero energy, cost-effective zero energy, imagine this, a 2x6 wall with R19 in it. Boy, if we went back to 2x4 with R10 on the outside, we'd end up with overall better performance at the same wall thickness. So that's really what we want to do, is help you optimize the performance and the cost associated with these elements. But that effective R value is what we're looking for. And when we talk about insulated sheathings, it could be foam, it could be mineral wools, lots and lots of choices out there that you want to work with, lots of options. And which ones do you want to use? You'll see some more and more manufacturers thinking about integrating it into the structural components, but pinks, blues, greens. Of course, you could get to SIP panels, which I'll talk about in a second, insulated concrete forms, lots of options to improve the performance of your walls. Steve, you talked about, how do I install that rain screen? Here's just a little example in an animation format of where we see things going. The simplest application of insulated sheathing, which most builders start with, is to think about simply adding a buck out to the windows. Whatever the depth of foam is going to be, not foam, but insulated sheathing, just buck out the window and then apply the foam or the insulated sheathing to that wall. And now the wall becomes very similar to what you're used to. Really, the only change is now your WRB, your weather-resistant barrier, is in fact just over top of that insulation product. Really, the only change becomes the length of fasteners, both for the weather-resistant barrier itself and for any cladding materials. And you would ask, well, can I nail through? Can I staple through? Well, certainly with the weather-resistant barrier, I can staple through back to the OSB or the structural sheathing. And then we need to think about the cladding system going over top. This doesn't get you to Steve's rain screen, but it's a very simple application. And every major manufacturer of engineered wood products and cement board products and plastic, if you will, vinyl products, or even brick would tell you, yeah, we have no problem going ahead and putting our cladding cladding system over top. And you'll notice the flashing details, windows, and so on are very, very similar. This happens to be one proprietary manufacturer, but lots and lots of choices out there to get you that proper flashing details. And it's really the only difference is you're going over top of the insulated sheeting. Now, your framers are going to push, sorry, your weather resistant barrier guys are going to push back, maybe your siding contractors. How do I know where the studs are? Because I would like to get back structurally to the studs. All right, I have to work out a process to get that done, measurements and so on. But otherwise, we're seeing a very common application of a weather resistant barrier over top of the insulated sheeting. And so with this, I would say recognizes the least change, if you will, to get insulated sheeting, continuous insulation to the outside. Notice the siding products just going on over top. So that's item number one. But I said we wanted to get to 2 inches of insulated sheeting or a continuous insulation on the outside. How do I get that done? Well, in this case, we would advocate for put your weather resistant barrier on first. That is, do your flashing of your windows and now install your insulated sheeting over top. Now it does mean I'm going to need some jamb extensions, an outside jamb extension. Now there are window manufacturers that are creating new flange locations that will accept inch and a half of insulated sheeting to the outside. So we are going to see innovations coming, but we like this. You'll notice that the weather resistant barrier was that crinkled weather resistant barrier that gave us some drainage capability if water happens to get behind the insulation. But notice here, we're now applying a structural strapping. And so the structural strapping ends up being the nail base for whatever cladding material you want to put off. And when Steve said we want to end up with a rain screen, this is the wall you aspire to. This is the wall that thermally gets you to where you want to be from a zero energy, but more importantly, from Steve's perspective, gives you that rain screen, that 3/8 of an inch air gap or more. And I just want to dwell on that for a second. 3/8 of an inch is kind of a magical number. The 3/8 of an inch stops any capillary flow, water wicking up. 2, it gives us the ability to drain, really good drainage. And 3, anytime we're over 3/8 of an inch, we actually start to see some airflow, some drying, some venting in behind. Remember Steve said we wanted drying potential? That vent space gives us some drying potential in behind our cladding. This is the wall that you aspire to build somewhere in the next 3, 5, 7 years. As you increase the thermal performance of the wall, if you're using standard frame construction, think about managing getting that 2-inch R10 to the outside and then applying a rain screen. And now you have a really durable wall, really 100-year wall is what we're looking for. And of course, there are other systems. I would be remiss if we didn't talk about ICFs, of course, if we didn't talk about perhaps double wall construction, or if we thought about SIPs. I'm not going to speak too much about double wall, but I'm okay with double wall. The only thing to understand is the outside of the wall got even colder. So this wall needs to be even more airtight. That's why Passive House would say build really tight buildings at say 0.6 air changes, because they are advocating huge thickness of walls, very high levels of R values. So we want to make sure that exterior surface, it's very cold. We don't want any warm, moist air getting into it. The 2 others, ICF and SIPs, are contiguous products. No chance of condensation inside of those wall cavities because of the nature of those materials. The dew point's within the wall, but there's no chance of condensation actually within those walls. So ICF is a great product. We just need to understand its thermal performance. Whatever the foam or whatever the product is, and typically foam EPS, the thickness of that foam, and there are various thicknesses that you can get. Remember, the R value of concrete doesn't change. It's still only, what, 0.08 per inch or something like that. You're not getting a contribution out of the concrete, so you get your effective R value to the outside. And a pretty standard ICF wall is an effective R value of 22. So 2.5 inches of EPS foam on either side, that's an effective R value of 22. That's a great wall. That's useful in southern climes. In northern climates, we'd like you to be up a little higher than that, 25 to 30. So maybe I go to a little thicker ICF. Of course, I'm a big fan of SIPs all at once. As you start to think about high performance walls, imagine getting your structure and the insulation all in one. And again, the effective R value, given the structural capacity of these walls. I'll just play a minute of this. Oh, sorry, my apologies. Yeah, a second of this animation that just shows the magic of ICF and of SIP panels and how important that can be. So, all of the proprietary systems, you'd want to work with the manufacturer of these products, but showing the nature of these products and the panelization. It does mean a little pre-planning, right? As one builder said to me, it made me a much better planner. It made me a better builder because I didn't want to have to make as many changes when I'm doing that SIPs, but he said it improved my overall performance as a builder because I pre-planned window opening sizes, had a better sense from my other manufacturer supply as to actually what was heading on. So I'll just show, as I say, just a little bit of this animation. And this is proprietary fasteners and typically proprietary splines. That is, they'll give you details of how to work out the installation practices for these products. And they're showing an insulated header. Isn't that kind of cool? Steve, you talked about getting rid of headers, but when I do need that structural header, wouldn't it be nice if it was insulated, is where we want to get to. So we won't play that for too long, but I just thought I'd give you a quick sense of that. And there is a great association, the SEPA, the Structural Insulation Panel Association, that could help you with the details of these kinds of products. So there you have it there. And so as we think about, just as a bit of a summary, think about the new metric is effective R values. It's no longer nominals, it's effectives. And you think about good fibrous installations, very, very cost effective. I just need to make sure I'm optimizing the performance of those properly installed, as Steve mentioned, but then continuous installation of the outside. That R25 to R35 is what we're looking for in climate zone 5 and above, effective R values, and effective R values of 20 to 25 in climate zones 4 and below, And we need to think about respecting the science of dew points such that we're not going to have condensation in walls. And we do that either by making walls more airtight or by adding insulated sheathing to the outside. And the good news is lots of strategic partners, NAMA members and others who can help you manage the process of getting to higher performance walls. And Joe, hopefully that gets us back to questions from the audience. Steve, you may have some comments as well.